All right, so you're supposed to compare three different things. Let me just give you some for examples here. Okay, imagine the Ferris wheel, right? Okay, the Ferris wheel has a period. That's the time it takes to go around once, right? So solidly, we could figure out the centripetal acceleration. A is 4 pi squared r over t squared. You can look up the radius on the website. We can measure the period with your cell phone at the park. You can write it down. This would require a data table and prior planning, right? Okay. And then you could take that acceleration and divide by 9.8. And let's suppose you get zero point 0.2, for example, right? Okay, 0.2 g's in the end, right? Which would be about 2 meters per second squared, because that's about 10. Okay. The second thing you could do is you could ride it with your accelerometer, How do you spell accelerometer? Am I still writing accelerometer, right? So that little thing, right? You would hold it vertically on the ride. Now, if you'd need a sensitive accelerometer to tease out a 2/10 of a g, but you can do it. Okay, that would be not very elastic, or very elastic, very easily stretched cord. And you'd look at the thing at the top and at the bottom. Okay, and you'd look at a thing, right? So at the top, for example, you might expect it to be I think it's, what is it, 0.8 Gs, right? At the bottom, you might expect it to be 1.2 Gs, right? Because at the bottom it's a bit more, at the top it's a bit less, and the difference being the ride, right? So this is 2/10 less than 1 G. This is 2/10 more than 1 G, right? Okay. The other way you could do it is you could get LabQuest data. You could get LabQuest data, right? You'd request that. Now we already have LabQuest data. I think we got some excellent data in like 2012 or something like that. And the LabQuest data would show the G-force doing this, just kind of a subtle thing, right? And you would expect that G-force would vary from some average by 2/10 of a G, right? Now it's going to be in meters per second squared, so again, you'd have to divide by 9.8. So when you do your comparisons, make sure that the acceleration here, that you get it in G's. Your accelerometer is naturally going to give you G's, right? The LabQuest data, you'll have to divide by 9.8 and get G's. Okay. You could even do this. You could even look at the thing going around in a circle. Okay. And there's a way to do it with video analysis. Okay. Okay. So there's even a fourth way to do this. So the Ferris wheel is pretty simple. It's a pretty easy one. We're expecting some slam dunks on this thing. Okay. So you can click on that thing, and I would just pick a spot here, like maybe from here to here, and pick one of the carts and click on that, and you ought to be able to get the acceleration, the centripetal acceleration from that. If you look at the video analysis stuff for the Ferris wheel, I'll show you that. Okay, so that's the Ferris wheel. That's one example. Okay, let me show you another example here. Okay, let's suppose you're looking at the Screaming Eagle, right? This big ride with a pendulum. It's got this thing that spins around, and this thing swings like this, right? Let's imagine that you decide, instead of figuring out the G-force, let's figure out the length of this, right? The length would be the length of the pendulum from here, from the pivot point to where you ride, okay? Which, by the way, is also the radius of motion here. So way number one is you could do a photo measurement, right? You could also do, you could also look at the spec sheet, right? You could get that from the spec sheet. I've got really good images from the actual design, okay? Way number two would be you use the formula for the period of a pendulum. This is in those videos, right? You could go T is 2 pi, the length of the pendulum over gravity, the square root of that, right? So measure how long it takes to swing from here back to here again. That's the period. Put 9.8 in for G and solve for L. Find the length of it, right? So this is one way. This is two ways, right? Let's find the length another way. The third way is to look at the G-force, right? You're moving at some velocity there, right? Okay, so go get the accelerometer data, right? That'll give you the acceleration, right? Right? And we know that the acceleration is v squared over r, right? Okay. And so if the acceleration is v squared over r, then if you know the velocity squared, and this actually is a little bit tricky because there's the speed of the pendulum moving this way, but there's also this thing is rotating, okay? I'll talk about that in the Screaming Eagle video. Okay, this thing's rotating, so your speed at the bottom is the speed of the pendulum plus the speed of that rotation, right? Okay, but if you look at that, you ought to be able to figure out that speed. We know what the g-force is, right? And then you could solve for r. R is, of course, the length of this ride. Okay, so you could find the length 3 different ways. That's crazy, huh? Here's another example. How about the big pink slide? You walk up to the platform and the big pink slide goes doo-doo-doo, and then at the bottom you slide and you slide to a halt, right? Let's suppose you want to find the speed that someone has, okay, at the bottom here. Final velocity, right? One way to do it is to predict it with conservation of energy. You could say the potential energy becomes kinetic energy, right? Whoops. Okay. mgh becomes 1f/mv squared. Now, this is assuming that there's no force of friction, so this gives you an interesting thing to talk about, right? I would expect this velocity to be much higher than the actual velocity because you're losing a lot of energy to friction, right? Okay. So you could find the final velocity that way, right? V is something, right? You could use video analysis, right? Video analysis. Right, and you could sit there and look at this distance, this thing there, and click on them for a few times, right? Okay, and if you know the length there, and we do know the length, right, you could find the velocity that way. Here's another way to do it. Okay, if you get the g-force, you could ask for axial g-force, right? Is you hold your accelerometer that way. You could measure it with your accelerometer, right? You could do it with the LabQuest. Okay, we could gather that data for you. You would just say, okay, I want the acceleration here at the end. Well, let's see, now you know the acceleration. How do you get the velocity from that? Well, you could figure out this distance here, right? And use the formula v squared is, let's say final velocity here. I'm using general physics notation here, plus 2ax, okay? So you know the distance over which it decelerates. You know the g-force, right? The acceleration here. Make sure that's in meters per second squared. So if it's in g's from your accelerometer, multiply by 9.8, right? And then you could figure out, in this case, the final velocity is 0 because you stop. You could figure out the velocity that way. Okay, I'm just trying to, just shake things up here. These are examples of 3 things, right? The velocity from conservation of energy, velocity from video analysis, the velocity from your LabQuest data or your accelerometer data, right? Yay.